Good morning, students, to a short session on chemistry in which we will be discussing a often confusing and difficult to grasp concept to many students, that is stereochemistry. In particular, we'll be looking at the chair conformation of cyclohexane. Right? Um, Specifically, we'll be looking at the reasons as to why a particular substituent prefers a position on the chair conformation via the 1,3 diaxial interaction. So before we get into the dynamics and the reason behind this, I think a little introduction is in due. So my name is Ritvik Kumar, and I graduated from IIT Bombay with an integrated master's in chemistry. Specifically, I majored in organic chemistry courses. So my inclination are towards organic chemistry. Now, with that comes some kind of experience in tackling some of the issues you may face during your journey to conquering JEE. Now, why did I become a teacher? What was my motivation? What is my motivation and my aspiration as a teacher? My motivation was purely chemistry. I loved chemistry since high school, at the very least. And I wanted to, explore more of it. And by being a teacher, I could give back in some form. Also, as a teacher, I'll be able to encounter more questions that further make me question about my own understanding of chemistry and maybe even make it better. As to my aspiration, it's to dispel this perception that chemistry is a subject of exception is the rule, right? I mean, we all have that difficulty, me including. Sometimes the explanations can seem very catered towards that problem, not very universal, like in physics. I want to find compelling reasons to describe those issues so that students are more convinced that chemistry has a more scientific basis to its explanations. So with that out of the way, let's look into the chair conformation of cyclohexane. So let's look at the two different forms of chair that we can draw. Right, so we have these two different forms in which we can draw the chair conformation, and they are interconvertible through rotation about single bonds. Now, why is it that, for example, if we have a methyl group, on carbon 4, as I've numbered in this left structure, if we were to draw its equivalent chair conformation in the other form, the axial methyl group, in this case, it's in the axial position, becomes the equatorial position. Now, what makes one conformation preferable over the other? This is what we're trying to explore in this, right? So we will just preemptively say that it prefers the equatorial position rather than the axial position. Now, why is that the case? Let's look into the Newman projection of this structure. So we will be drawing the Newman projection along the C1, C2, and C4, C5 bonds. To have a better understanding of how this functions. So looking at the different bonds here, these are all hydrogens on the left-hand side. And we have hydrogens here with our CH3 group here. So if we compare the axial bonds that will be placed here, we can see that the atomic radius for the CS3 group, as it becomes more bulky, right? If we replace the CS3 with an ethyl group, this will cause a steric interaction with this. A steric interaction is basically an interelectronic repulsion, which will cause some amount of destabilizing force on the molecule. Now, why is it that we have interelectronic repulsion in the axial case, but not in the equatorial case? Let's look at the structure for the other chair conformation to have clarity on so in this case, I'll be drawing it along C1, C6 and C3, C4. So the remaining all bonds are hydrogens. Let's keep it as such. And we have our methyl group in the equatorial bond in this case. So what do we have here? We have a gauche interaction with the hydrogens. But remember, these bonds are away from the system, meaning the three bonds, hydrogen and this methylene group here for carbon 4 is coming towards us. So when you look at both the methyl and the hydrogen, which are showing gauche interaction, they are pointing away. So as you can see, this is pointing away. Hence, their interelectronic repulsion is going to be minimal as this becomes larger. As the methyl group is substituted by an ethyl or tertiary butyl, they're always pointing away. Hence, the interelectronic repulsion or the steric interaction is lesser as compared to in the case when it was in the axial position, where it is parallel to each other. So the more bulkier it gets, the closer it becomes to each other. So this is why we prefer the axial, or we prefer the equatorial over the axial. And we can safely say the equilibrium constant is greater than 1, favoring the right-hand structure. So whenever you have a bulky group, the more bulkier group, you will prefer to place it on the equatorial rather than the axial. This is the idea of 1,3 diaxial interaction playing a role in the stability of the chair conformation. Right? With more exciting chemistry until the next session, this is me, Ritwik Kumar, signing out.